just hit the record button while I do that. I am pleased to present Dr. Robert Rogers, who is a lead meteorologist at the NOAA AOML Hurricane Research Division. And he's going to talk to us about advancing the understanding and prediction of tropical cyclones using NOAA aircraft observations. I see that a few folks are unmuted. As a courtesy to our presenter, please mute your mics. We will take questions in the chat box at the end. So at this time, let's go ahead and mute your mics. Otherwise, I will start muting folks. Rob, take it away.
Okay, thanks, Shirley, and thank you for giving me the opportunity to talk to you all today about something that's really important to me, as I think it really forms the core of what we do at HRD, and that is collecting data using aircraft and using the data that we've collected to better understand and predict tropical cyclones. So before I get started, I'm just going to go ahead and shut off my camera, just so you're not distracted by my face, and then I'll turn it back on when we take questions. Okay. So let's go ahead. So just a brief outline of what I'd like to talk about today. I'm going to talk a little bit about just the history of airborne hurricane research within NOAA, and then talk some about the tools that we use, the aircraft and the instrumentation that we use to observe hurricanes. Then I want to talk a little bit about what what's really formed the focus of our data collection activities since about 2005. That's the intensity forecasting experiment. And then highlight some of the recent research that arose out of our IFEX efforts. Then I'll take us on the plane to talk a little bit about some of what a bit about what it's like to be on the aircraft, showing some pictures and videos of hurricane missions. And then finally look toward the future to talk about what our next generation field campaign effort called AFEX looks like. So I guess the first question that I'd like to talk about is, why are observations important? A lot of very important physical processes within hurricanes span scales that can cover many orders of magnitude, ranging from thousands of kilometers, the size of a continent, to fractions of a millimeter, little tiny microphysical particles and so forth. Observations can span all of these scales, and they really are a key component of what I'd call a balanced approach that includes observations, modeling, and theory toward advancing our understanding and improving our forecasts of hurricanes. They allow us to, or they provide real-time information on hurricanes, and they allow us to assess the performance of the numerical models that are so important in our forecasting, as well as providing a check on the theories that have been advanced in the community. Now, there are three primary platform types, platforms that are in the air: airborne platforms, spaceborne platforms, satellites, and land-based. But I'm just going to focus here on the airborne component, because that really forms the crux of what HRD has done for decades, actually. So just a brief history of airborne hurricane research in NOAA. Back in the mid-1950s, in 1954, there were a series of devastating hurricanes, Hurricanes Carol, Edna, and Hazel, that impacted the Mid-Atlantic and the New England states. And I think that included Washington, D.C. Perhaps not surprisingly, as a result of that, the National Hurricane Research Project, or the NHRP, was created 1 year later. Routine airborne hurricane research missions got their start during that time. NHRP was formalized into a research lab called the National Hurricane Research Laboratory in 1960. Project Storm Fury, that some of you perhaps have heard of, which is a hurricane modification experiment, began shortly thereafter. In 1983, NHRL became a division within AOML, as Shirley talked about, in Miami, and it was renamed the Hurricane Research Division. At the same time, Project Storm Fury came to an end. About 20 years later, in 2005, there was a decision to really change the focus or place a greater emphasis in terms of the airborne data that we've collected on improving our prediction of hurricanes. So really focusing on the prediction side of things, and in particular, focusing on improving our prediction of hurricane intensity. I'm going to come back to that a little bit later in this talk. So what are some of the tools that we use for observing hurricanes? Well, the primary platforms that we have three aircraft within NOAA. We have two P-3 aircraft. They have nicknames too. One of them is called Kermit, was built in 1975. The other P-3 is called Miss Piggy. That was built 1 year later in 1976. So they've been around for quite a long time, but obviously we take very good care of them. And in fact, both of those P-3 aircraft just got new wings, new engines, and new avionics within the past few years. So that's effectively extended their life cycle for about another decade or so, at which point we'll replace these aircraft. Another aircraft is called Gonzo. That's our Gulfstream 4, our G4 jet. So the P3s are primarily responsible for sampling, the inner core, eyewall penetrations at relatively low altitude, whereas the G4, which I'll talk about a little bit more, flies at higher altitude, about 42,000 feet, and it primarily samples the environment, but it does, from time to time, sample over the core of weaker systems, and then it gets up near the inner core as well for stronger systems. So all three of these platforms are very crucial in terms of the data collection that we conduct. So what are the instruments on the aircraft? The primary instruments on both the P3 and the G4, we're going to focus here for some of this on the P3 though, include in situ instrumentation. So basically these are the instruments that are mounted directly on the aircraft, and they give us measurements of things like the winds and the temperature and the moisture and the pressure. And so these are just a couple examples showing just time series of what the winds look like if you go from the center of the storm on the left, and then you see the winds peak at where the radius of maximum winds occurs, and then the winds tail off as you get to larger and larger distances from the center. And the temperature shows a very common structure in hurricanes, particularly a warm core structure. So it's warmer right at the center of the storm, and then that temperature decreases as you go further out. So these are really important instruments or measurements that are taken at flight level. Another type of instrument are what we call expendables. So these are instruments that we launch from the plane, and essentially they collect their data, report them back to the plane, and then they're lost. So that's why they're called expendables. And so a dropsonde is one of the most important expendables that we have on both the P3 and the G4. So this is just a picture of what a dropsonde looks like. It's a tube that we launch from the plane. I'll show you a video of what that looks like a little bit later. And as that tube leaves the plane, a parachute opens, and the dropsonde falls to the surface relatively slowly. And while it's falling, it's recording things like temperature, pressure, winds, moisture, and reporting that back to the plane. It takes these measurements at a very high frequency, so it's very important data that allows us to get information not just at flight level, but below the flight level down to the surface, including right at the surface, which obviously is very important in terms of assessing the intensity of the storm. Remote sensors are another set of instruments that are very important for what we collect. Tail Doppler radar is one. So there's a picture here on the left. You can see the antennas, two antennae on the tail Doppler radar, or the TDR, on the G4 aircraft. There's also something called a step frequency microwave radiometer. That's an instrument that measures the brightness at the surface of the ocean, and from that we are able to infer what the surface wind speed is, which is of crucial interest to the National Hurricane Center. And then other instruments such as the scanning radar altimeter, which gets us a sense of what the wave field looks like, and a Doppler wind LiDAR. So this is a picture on the right showing what the LiDAR looks like mounted on the side of a Navy P3 aircraft. And then finally, I'll talk about this a little bit more later, but uncrewed instruments are a relatively new development that we've really embraced and are taking advantage of as best we can. These include what we call small uncrewed aerial systems, or SUASs. So here's a picture of one of our scientists, Joe Cione, holding an SUAS, just to give you a sense of what the size of that is relative to the aircraft itself, the P3 aircraft. So that's an instrument that's launched from the P3, and then it's piloted as it descends to the surface, collecting measurements. There's also autonomous underwater vehicles, or AUVs. Ocean Glider is an example of that. And then there's also sail drones. So here's a picture of a sail drone. So that's something that actually is autonomously driven, and it collects both air temperature, atmospheric measurements, as well as ocean measurements as we essentially pilot the sail drone for long periods of time and over great distances in the oceans. So what are some of the key instruments on the aircraft? So I mentioned the P3 and the TDR. There's also another radar called the lower fuselage radar. So this is a picture of the P3, and so that circle is showing you what the LF, or the lower fuselage, or the belly radar is another term that we have for it, underneath the aircraft. And that's a radar that scans horizontally as the plane is flying. It's giving us a mapping of basically the reflectivity in the rainfall field. And so this is just an example of an image that we can get from the LF radar. This is a case showing, you see the eye wall. So the warmer colors, the yellows and the oranges and the reds, are showing you the heaviest reflectivity, the heaviest rainfall. Usually the strongest winds are located in the eye wall. But you also see these spiral type structures, which are the spiral rain bands and secondary eye walls that sometimes we can see in these hurricanes. And so The ELIF is a really important tool for giving us a mapping of what the structure of the storm looks like in the inner core. Tail Doppler radar, I mentioned that before. So this is an invaluable instrument that gives us measurements of the three-dimensional wind structure within the inner core of the storm. So this is just an animation showing you what it looks like. So the blue dot is the aircraft that's flying through, a mature hurricane. Here you can see a nice depiction on the satellite imagery. And then the shading is showing you wind speed that we're able to collect. It collects a swath of data as that aircraft makes a pass through the center of the storm. And then on the right, you can see an equivalent vertical cross-section of what the winds look like as the aircraft is passing through the center on an inbound and into an outbound leg. And so, again, this is very valuable information that gives us a nice three-dimensional picture of what the inner core looks like of the storm. And we've actually perfected, or we're continually developing the computer code to analyze and process this data. So we've gotten it to a point now where we can actually quality control and synthesize and analyze these data and produce these three-dimensional analyses very quickly within 20 minutes of completing a pass. Typically, we can give this information to the Hurricane Center and to researchers. I've already mentioned the GPS drop sonde, so this is what it looks like, and these are just examples of some of the types of data we can get from a sonde. So these are profiles of 3 different sondes that were launched in rapid succession across the eye wall of a major hurricane. So we're having measurements from the aircraft flight level at about 2.5 to 3 kilometers, and then as the sonde is descending to the surface, you can see very high frequency measurements in the order of 4 hertz, or 4 measurements per second. That gets reported back to the aircraft, and so that really allows us to resolve a lot of detailed structure in terms of the wind field as well as the temperature and the moisture field as the sonde is descending to the surface. In this particular case, you can see the blue sonde, or the sonde denoted by the blue line, is actually capturing Category 5 wind speeds in the lowest 1,500 feet just above the surface as the sonde is splashing into the water. I mentioned the SFMR. So again, that's an instrument that measures the brightness of the ocean surface from which we can infer the surface wind speed. So what I'm showing you here is in this middle panel is the blue line is the track of a hurricane through the Gulf of Mexico, and the red line is showing you the flight track of the P3 through the center of the storm. And then on the right, you'll see time series of flight level winds in red and SFMR surface winds in black. So you can see these little spikes, and each time you see a spike, that represents the P3 flying through the core of the hurricane and passing through the eye wall. That's where the winds tend to peak. If you also notice the surface winds, the black lines tend to be a little bit lower than what we see at the flight level. That's a common characteristic. And typically, the surface winds are a little bit weaker than what we measure at flight level, depending on the altitude that we're flying and so forth. But that's usually a structure that we see. But again, the SFMR is a really important tool for real-time assessment of hurricane intensity. So I've talked a little bit about some of the key instruments, platforms, and instruments in observing hurricanes. Well, how do we use this information, or what do we do with this data? So I mentioned back in 2005, there was a shift in our emphasis toward prioritizing improving our prediction of hurricanes, in particular hurricane intensity. And so the reason that we made the shift is illustrated by this graphic here. So it's a little bit old, but these trends essentially, I think, hold even up to 2021 or so. But what I'm showing you are intensity forecast, or forecast errors, I should say, from the National Hurricane Center official 48-hour forecast. So going back to 1994 and going up through 2018. So if you just look at 1994 and you say, okay, let's just normalize our error and call that a value of 100, how has the 48-hour track error changed over that time period, and how has the 48-hour intensity error changed over that time? So if you look at the green line, it's showing you how the track error has improved, really. You see a substantial improvement in our 48-hour NHC track forecast, such that the track forecast errors have reduced by about 70%. Compare that with the intensity error, certainly you see improvement, but it's not nearly as quickly an improvement as what we saw with the track forecast. It's only a reduction in our forecast error of about 30%. Now, if you just sample only those hurricanes that underwent rapid intensification means a storm that intensifies 30 knots, or about 30 miles per hour or so over a 24-hour time period. So it's the equivalent of going from a Category 1 hurricane to a Category 3, or a tropical storm to a Category 3 in a short amount of time. So it's a real forecast challenge, and it's a forecast nightmare, but it's also a research challenge. And the forecast challenge is illustrated here. If you if you look at only those hurricanes that did not undergo rapid intensification, looking at how the errors had, 12-hour forecast error, up to 48-hour, up to 120-hour, just focus on the 48-hour forecast time. Non-rapidly intensifying hurricanes had errors on the order of about 8 knots or so. So that's pretty good. But if you look at the cases that underwent rapid intensification, it's greater than 25 knots. So it's a huge forecast error. And in fact, intensity forecast errors for rapidly intensifying hurricanes was 3 times greater than the forecast error for non-rapidly intensifying cases. So there's a need to just overall improve our intensity forecast, and in particular, there's a focus on rapidly intensifying cases because that's where our greatest error occurs. So these observations, or these statistics, really motivated this emphasis toward improving our prediction of storm intensity. Why is predicting storm intensity such a challenge? Well, this is just a cartoon showing you, the structure of a typical hurricane, a vertical slice through the storm. And you can see a lot of structures. You see the eye, you see the air, the air spiraling in, and you see coming into the eye and ascending out, and then outflow in the upper levels. But you see a lot of detailed structure here. But structures have process sets occurring with them, and these processes occur over a variety of scales. I talked about that at the beginning, right? You can have, upper level, troughs. You can have vertical wind shear that might span thousands of kilometers, all the way down to how the vortex is organized on the 100-kilometer spatial scale, and even where the convection is located and the structure of that convection, maybe on the 1 to 2 kilometer scale, and even turbulence scale, and air-sea interaction, sea spray, and microphysics, and so forth. So it's a very complicated and dynamic environment here. These are just the examples of the types of scales I'm talking about. But, to get an intensity forecast, you have to consider all of these scales and how you characterize those structures and how you understand the interactions of these processes and these structures within scales and across scales are really key to improving our forecast, and how you represent them in the numerical models in particular. That's a really key step in improving our forecast. And as hopefully I've convinced you, airborne observations are a key tool in that, and they really provide a unique opportunity to study these processes across scales. So with that said, we did reorient our field campaign toward, again, improving intensity forecasting directly, but there were 3 primary goals that we followed to achieve that. IFEX was the name of the experiment we came up with, the intensity forecasting experiment. And IFEX was intended to improve the prediction of TC intensity change by, again, supporting these 3 primary goals, which I grouped into what the first one I call sort of a model development focus. And so that is collecting observations that span the TC life cycle across scales. So from the environmental scale all the way down to the cloud scale and the even smaller scales. And that information is used to better initialize models as well as evaluate and improve models. The second primary goal is what I call nowcasting. And so that is what allows us to observe the structure of an existing hurricane, tropical cyclone, and ultimately to develop and refine measurement technologies that, again, provide and improve real-time monitoring of TC intensity, structure, and the environment. And then finally, what I call research, and that's more the hypothesis-driven type of work that a lot of us do at HRD and within the broader community. And that's really focused on improving just our understanding of the relevant and important physical processes that govern intensity change for a TC at all stages of its life cycle. So not just mature hurricanes, but tropical storms and tropical depressions and even pre-depressions. Why do some storms develop and others don't? That's an important and key question. So all 3 of these goals are really important, and they form the underpinning of what we did in our IFEX efforts over the period from 2005 to 2020. So I just want to give you a couple examples of some of the advancements within each of those goals. So that first goal focused on model development. One of the primary goals there was to better assimilate the data into the numerical models. So we go out and we collect observations of the storm and of its environment, and then we have to send that information to the operational modeling centers, and then that information is used to tell the models what the initial condition or what the initial structure of the storm and its environment are, and then from there they integrate forward in time. That's basically what a numerical model does. So this is one example of a series of missions that we conducted in Hurricane Harvey from 2017. So these lines here, I'll show you, I'll talk about this a little bit more later, but these are the typical flight patterns that we will conduct within the inner core of a hurricane using the P3. So each of these little white circles are center fixes, so as we're identifying what the pressure of the storm is, and then you see the winds and so forth, the information from the TDR and all that is transmitted in real time. So this white box is showing you a domain from which we produced an analysis of the wind field from the TDR data. This is just an example of winds at one altitude that we were able to get within the inner core from the TDR data. Then information is transmitted again to the ground and incorporated into the operational forecast models. And then this is the result of what we can produce from the models when we incorporate that information from the TDR data. So this is a basin scale HWARF forecast of reflectivity from Hurricane Harvey. So the shading is showing you just the rainfall looks like, and then the black symbols are the actual observed position of the storm. And so you can see that this model did a very good job at capturing the landfall location of Harvey, the stalling of Harvey in Texas, and then how it moved back out over the water and then up parallel the coast. So we've seen significant improvements in our forecasting capabilities as a result of the assimilation of this data that we collect from the aircraft. Another example of how we can improve models with our aircraft observations is looking at evaluating the models and identifying flaws in the models and ultimately improving how processes are represented to make a better forecast. And so this is one example showing you radial inflow. So this is the flow that comes into the storm in the lower levels, and it goes up in the eye wall basically, and then it goes out in upper levels. So if you just focus on the lowest 2 kilometers or 6,000 feet or so, that's what we call the planetary boundary layer, the PBL. And so this shading here is showing you inflow, so flow into the center of the storm. So this is a radius height. So on this y-axis is going up to 2,000 meters, and this x-axis is basically a measure of radius going out to 3 times the radius of maximum winds. And so the strongest inflow from observations from the drop zones that we've collected over many different, thousands of drop zones over many different storms, we composite all that together and we have this composite structure of the radial flow in the planetary boundary layer. So you can see that the inflow is maximized right at the radius of maximum winds, and the depth of that inflow is indicated by this black line. Goes out to about 1,000 meters or so, 1 kilometer depth, and then it increases to about 1.5 kilometers when you get out beyond the radius of maximum winds. Well, we've run various configurations of the operational model back from all the way back in 2011, and then with each successive version of the model, we've improved the model based on modifying how mixing occurs within the boundary layer, and by modifying the mixing formulations based on observations, we've actually been able to improve how that boundary layer structure is represented. So this far right panel, this PBL 16 to 19, this is the version of the operational model that uses the best representation of these mixing processes based on the observations we've collected. So the older versions of the models had a much deeper and stronger inflow, very unrealistic compared to what we observed. But by the time we got to this more updated version of the model, now you can see that inflow structure is much better represented. And I don't have time to show it here, but we've actually done tests looking at rapid intensification forecasts, and by using these improved formulations, our RI forecasts have improved as a result. So this just really highlights what I'm talking about here. So if you look at the HWARF again, which is the operational forecast model that NOAA uses, this is showing you intensity skill. So values greater than 0 indicate an improvement in the forecast based on some benchmark, and values less than 0 indicate a degradation. So the earlier version of HWARF from 2011 to 2013 shows some improvement in forecast skill out to about 36 to 48 hour lead times. But once you get beyond 48 hours, the forecast skill drops off significantly, such that we actually are quite a bit worse at 5 days. The intermediate stage, the green line here showing you a more recent version of the HWARF model, does show some improvement, especially at those longer lead times, but you still get a degradation in the skill beyond 4 to 5 days. But now look at this blue line, that the most recent version of the HWARF model shows substantial and dramatic improvements in our forecast scale relative to a baseline for all lead times out from 1 day up to 5 days. So it's really a remarkable improvement in our forecast skill. And I would argue that at least some of that has arisen from the data that we've collected and the improvements in the models. Of course, there's other sources too, improvements in the models themselves, including the resolution improvements and so forth, but the data certainly has played a role in that. And this illustrates that point that I'm making. So what I'm showing you here now is a skill plot of the intensity forecast skill. When you go back and you run forecast and you exclude the aircraft data. So you run forecast with the aircraft data, and then you run the forecast without the aircraft data. And so the black line is showing you the improvement in the forecast skill when you include the aircraft data for all lead times out to 5 days. And so, at least out to 96 hours, so at least out to 4 days or so, we do get an improvement in the intensity forecast skill just by including aircraft data, by as much as close to 15% improvement at the 48-hour lead time. So a clear indication that the aircraft data itself is providing helpful information to improve our forecasts. So let's talk a little bit about some examples of NOWCASTS. So this is the second IFEX goal, and this really allows us again to provide an improved representation of the tropical cyclone structure and intensity, which then we report back to the Hurricane Center. And so we've developed, in working with Hurricane Center scientists, the ability to incorporate aircraft data into the operational visualization tool. So AWIPS-I is the tool that they use at the Hurricane Center in real time. The specialists use to look at forecast guidance and observations and so forth. And so we have the ability now to look at the aircraft data. This is an example of one such visualization. This is showing you TDR data, tail Doppler radar data, a swath of data. So the colors are different wind speeds at I think it's 2 kilometer altitude, maybe it's 1 kilometer altitude. And then the little, the white, it's kind of hard to see, but if you can see these little white plus signs, plus and minus signs, this is lightning that's detected from, we can either use satellite detected lightning or ground-based lightning detection networks, but we're able to map those onto the same grid. And so you can see where the lightning is occurring relative to where the strongest winds are. And that's a really powerful forecast tool, but both to assess the structure and also to predict in the short term, at least, what's likely to happen in terms of the structure and intensity of the storm. Here's just another example showing TDR data in real time. So these are passes through the center of Delta from 2020. So these are just separate center passes or eye wall penetrations separated by about an hour or 1 to 2 hours or so. And so the shading now is showing you the wind speed, I believe at 2 kilometer altitude. And you can see how the wind is dramatically strengthening over the course of just about a 3-hour time period. So Delta is rapidly intensifying, and we're able to monitor and detect that with the TDR data that we can then transmit again in real time to the National Hurricane Center. So now I want to talk a little bit just about some of the research that's been done looking at better understanding important processes and intensity change. So I wrote a paper last year that kind of provided an overview or a summary of the research, at least over the past 10 to 15 years or so. And you can really group those into 5 separate categories. First one is characterizing the TC inner core structure and intensity change, just through kind of composite studies. Looking at TC intensity change and vertical wind shear. Looking at boundary layer processes. I've already shown you some examples of that in air-sea interactions. Secondary eye wall formation and eye wall replacement cycles. And finally, the genesis and development of weak TCs. A lot of the research, I'm just going to give you a couple of quick examples from each of those categories, one from each category. But a lot of that research focused on structures, again, associated with intensity change processes consistent with IFEX goals. And primarily, the research used tail Doppler radar and GPS dropson data. And they were done in both composite or multi-case as well as case study frameworks. And each of those approaches has their advantages and disadvantages. But I think they've all provided some helpful insights both to the research and the forecasting communities, I hope. So the first one is just characterizing TC inner core structure and intensity change. So this was a paper that was written about a decade ago where we looked at composites in hurricanes that were intensifying and hurricanes that were not intensifying. We basically looked at what the wind field looked like. And so if you just look at these bars, the top panel is showing you intensifying hurricanes, and you can see that the bar, the peak in the bars, which is showing us where the strongest thunderstorm activities are occurring relative to the radius of maximum wind, which is the value of 1 here. So in the case of the intensifying storms, that the peak in the distribution of the strongest thunderstorms is inside the radius of maximum winds, whereas for non-intensifying or storms that are steady state, that peak occurs well outside of the radius of maximum winds. So there's a difference in that radial distribution of strong thunderstorms that we think plays a role in determining whether a storm intensifies or not. Another example, looking at TC intensity change in vertical wind shear. So this is just a cartoon that arose out of a study that looked at a couple different cases that were experiencing vertical wind shear or change of wind speed and direction with height that tends to be unfavorable for intensification of storms, but in some cases, the storm can fight back against that shear and intensify. And so we looked at two different cases, one that did intensify and one that did not, to try to understand what were the differences in the structure of the storm. And so this cartoon is basically showing you what some of those key differences are. And I won't describe all the details here, but basically, I just want you to know that the storm that did intensify, this Bertha, actually had a more symmetric distribution of rainfall precipitation around the storm. It wasn't just on that downshear side, but it actually was able to get to the upshear side. And so, a question is, why did that happen? And so that's what a lot of the research that we've been doing lately is focused on, those types of questions. But nonetheless, these differences are important structural differences that we've been able to identify. Boundary layer processes and air-sea interactions. So this is another composite study using the dropson data. So we took, again, dropsons from many different storms, thousands of dropsons, and we just looked at what is the structure of the temperature and moisture field at the surface, or right near the surface. What does it look like if you rotate everything relative to the direction of the vertical shear? And so the vertical shear vector is this black arrow, it's pointing up. So and then the warm colors are showing you where you have warmer and moister air in the boundary layer, and then the cooler colors, the blues and the greens, are cooler and drier air. And so what you can see is that you tend to get cool and dry air inside the eye wall, or the radius of maximum winds, primarily left of the shear vector and on that upshear side. But as you continue to travel around the storm, you start to see that the air moistens and warms, mostly through the transfer of energy from the ocean to the atmosphere. So as that air spirals back around, it recovers a lot of that energy that was lost to downdrafts, to the point that you can sometimes get the development of new thunderstorms on the downshear right quadrant. So it's this kind of cycling idea that we were able to identify from observations, and also produce in numerical model simulations. Another aspect we've looked at are secondary eye wall formation. So that's basically where you have a primary eye wall, but then sometimes you can get an outer eye wall that will develop and choke off essentially that inner eye wall. And so typically what happens is the storm will weaken temporarily while that outer eye wall develops, but then that outer eye wall starts to contract. And when you get that contraction, the storm starts to intensify. So, an important research and forecasting question is, when will we get that outer eye wall develop? And so these observations are showing you, using tail Doppler radar data, this is 3 separate passes through the center of a storm, separated again by about an hour and a half time period. And so you can see that the contours here are showing you the vertical velocity, so the upward motion. And so you can see the development of the secondary eye wall developing, over a pretty short time period. And so we get information on the detailed structure of the outer eye wall as it's developing, and then we can diagnose some of the physical structures. And then finally, looking at genesis and development of weak TCs. This was a paper that was published a couple of years ago, looking at a storm that weak, like a tropical depression. It was very disorganized. You had a low-level circulation center and a mid-level circulation center that were displaced from each other. But over the course of about a 5-hour time period, you started to get the alignment of the low and the mid-level circulation centers. And so the question that we looked at here was how can we characterize that alignment process? And then what were some of the key processes underlying why the storm became better aligned? And so this is just showing you, documenting the alignment of the mid-level, the top panel, and the low-level center, and how that alignment occurred at the same time that we got really strong high echo tops and very strong thunderstorm activity, coincident with where that alignment occurred. And so I think some nice results came from that study. So let's go on the aircraft a little bit and look at what it seems like to be on the plane. So this, again, is a picture of the P3 in the back and the G4 in the front. The P3, as I mentioned before, typically, I think you'll see it fly in here, hopefully. The P3 flies at about typically about between 5,000 and 10,000 feet altitude for the most part, especially when it's making an eye wall penetration. And then the G4 comes in at a much higher altitude, about four times as high, about 40,000 feet, 42,000 feet. And again, the P3 is primarily responsible for flying in the inner core, punching through the eye wall, and the G4 usually will fly around the eye wall, but sometimes will overfly the center too. Where do the aircraft operate? So this is a map showing you primarily in the Western Atlantic, the Gulf of Mexico, and the Caribbean. This is a bit of an outdated map. Actually, now the Aircraft Operations Center is no longer in Tampa. It's in Lakeland, which is near Tampa, but not in Tampa. But anyway, So if you assume 2 hours that the plane can be in the storm, so obviously the further the storm is away, the less time on station you have, but assuming at least 2 hours on station time, aircraft operating out of Tampa or Lakeland area can cover most all of the P3 can cover most all of the Gulf of Mexico and the Northwestern Caribbean. But if you want to go further east, we need to move. We deploy to stations in the Caribbean, whether it's St. Croix or Barbados or even Bermuda. That gives us sampling along the Western Atlantic off the east coast of the United States. And the G4, it's a higher altitude jet, it flies much faster, and as a result, it has a much larger and longer range. So that if the G4 is located in Barbados, it can actually get more than halfway across the Atlantic Ocean. So that's really important. I think I'll talk about in a minute about some future work that we're planning here this season, actually. Typical flight patterns. So the P3, this left panel is what we call a figure 4. If you look at this diagram here, the numbers are just showing you waypoints along the pattern that a P3 will fly. So this is sort of like a backwards number 4. Butterfly is another pattern. It kind of looks like a butterfly if you imagine, but each of these patterns gives us different characteristics in terms of the sampling, how often we pass through the center of the storm, what the angular distances between center passes, and so forth. But they each have their advantages and disadvantages. And then a typical G4 set of patterns. Again, the G4 typically does not fly through the center or over the center, but mostly gets near the center and then flies around it. But depending on what we want to accomplish, we do these types of circumnavigations or star patterns. I don't know if you can hear it, but this is a video showing what it looks like to launch a dropson from the P3. So the operator will put it in a tube. It's a pressurized tube, and then actually releases, opens up the chute basically underneath the aircraft, and then the dropson gets sent out. And again, as that son is falling to the ground, to the ocean, it's reporting back all this information to the aircraft in real time, which then we report down to the ground. This is a picture of what it looks like to be within the eye of a hurricane. This is a Category 5 Hurricane George from 1998. This is illustrating what we call a stadium effect. So you can see, first of all, you can sort of see the curvature here. So that basically it's called a stadium effect because you imagine if you're in like the 50-yard line of a football field and you're looking all around you, and you can see the curving of the stadium. So this is kind of what I think initially it was called an opera house type of, I think the first person to describe this, but they call it stadium effect now. But again, it's a nice example showing you the eye wall features that comprise the stands within the stadium. And then right near the surface, you can see these low clouds right above the sea surface. So this is within the eye, and you get these really strong hurricanes. It clears out really nicely. You get strong sinking motion within the eye. And so that allows us to see some remarkable structures, for example, what you see here. This is just a video of what it looks like to be on a storm, or on the aircraft in a storm, showing a stadium effect. Again, you can see the curvature of the clouds. So this is a much larger eye than I think what I was showing you in the picture. But so what we're doing usually in the aircraft at this point is we're trying to hunt the center. The aircraft will find the center of the storm, mark that center, and then usually release a dropson to get a measure of the central pressure. That's really important information that the Hurricane Center uses to assess what the exact position and the exact intensity of the storm is. So let's look toward the future. So I've talked about what IFEX was for 15 years, but last year we decided to kind of broaden our focus a little bit. And the reason for that is illustrated by this table. I'm not going to read all the numbers there, but basically I just want you to know that over the past several years, there have been multiple billion-dollar TC-related disasters. Almost each of these storms had at least one period of rapid intensification, so that's still a challenge and something that we need to focus on. However, there are other significant sources of damage and death. Storm surge inundation, extreme rainfall, and high surf and tornadoes. They are significant contributors to the damage, in addition to the high winds. So just quickly looking at this table, in the case of Harvey, for example, Harvey produced over 60 inches of rainfall. Storm surge, Dorian produced over 20 feet of storm surge in the Bahamas, and Michael produced 14 feet in Florida, I believe it was. So it's not just, and Harvey produced 52 tornadoes. So it's not just the winds. It's really, it's the water, and it's the rainfall, the storm surge, as well as the tornado. So it's not just the winds. It has the broader category of hazards. So really that begs, I would argue, a new research focus that we want to undertake with our field campaign efforts. So focusing just on intensity forecasting, which is what we did at the inception of IFEX, is now a narrower scope, I argue, within a broader expanse of forecast challenge and knowledge gaps that we really must address. And so IFEX priorities have been broadened beyond intensity to include structure and hazards, with the focus of improving model analyses with the observations that we collect. And so as a result, we came up with this new acronym called AFEX. So it's advancing just the prediction of hurricanes. So it's a broader term, not intensity forecasting, but just generally prediction. 3 goals with AFEX, similar to IFEX, very similar to what we did in IFEX, but we have added some additional language in there in our goals, focusing on looking at the analysis of TC intensity, structure, and environment in goal 2, as well as the hazard assessment. And then goal 3, we still, that's still focused on more of the hypothesis-driven research, understanding the physical processes, but we're broadening that focus to include not just intensity, but also associated hazards. So I hear an echo, someone's not muted. Thank you. So one of the unique aspects of AFEX, and something that we're always doing, is we're trying to test out new platforms and instruments. And in particular, we're focusing on filling some key observational gaps. So I talked about SUASs before. This is a picture of one SUAS called the Coyote that actually was successfully demonstrated several times over the past several years. And so here's just a video showing what it looks like to launch a SUAS from an aircraft. So it drops out similar to what a drop zone looks like, but the sleeve falls away and you can see an actual mini plane. Basically, the wings open up and you have a propeller that starts on the back of the SUAS that allows the instrument to basically fly. So we have a crew on the aircraft that basically fly this SUAS as it is descending down to the surface and taking measurements. So these are just examples of some of the measurements that have been collected. This is one SUAS measurement in Hurricane Edward. On the left, we actually flew missions in the northwestern side of the eye, and it was as it was flying in, it gets into the boundary layer, and it's flying in the inflow basically of the storm of Edward as it's going into the center. And then on the right here is just showing you some time series of wind speed measurements from all the Coyotes that were released, I believe, in 2019. And so you can see, again, this is altitude going up to 1.5 kilometer altitude. So, these kind of stair-step patterns that the Coyote or the SUAS are flying as these are descending to the water, getting to altitudes that the manned aircraft really cannot safely do. In one case here, one SUAS measured winds of 70 meters per second, so 150 miles an hour at just 500 meters above the surface. So really valuable measurements that we otherwise couldn't get from manned aircraft. Another instrument is the compact Raman LiDAR. So that's a LiDAR that gives us retrievals of 3-dimensional fields of temperature, water vapor, clouds, and aerosols below flight level. So these are just some examples of some of the measurements that we can take underneath the aircraft within the boundary layer. It's very high resolution, 45 meters in the vertical and about 100 meters to 1,000 meters in the horizontal. And again, it provides very valuable thermodynamic information in the boundary layer. So this is a pretty new instrument for us, and we're just starting to look at this data, but I think it shows a lot of promise for some important measurements that we can't otherwise get routinely. Another type of LiDAR is called the micropulse Doppler LiDAR. And so this is a separate LiDAR that measures the winds. So the compact Raman LiDAR measures temperature and moisture. This measures winds. Again, using kind of LiDAR concepts. And what's nice about this is that this LiDAR complements what we can see from the tail Doppler radar. The TDR requires precipitation scatterers to give us measurements. So, but when you don't have those scatterers, you can't get those measurements. So this LiDAR and similar types of LiDARs can give us information that we otherwise wouldn't be able to get. So in addition to these new instruments that address observational gaps, we also have new sampling strategies. And so this is an example of one type of pattern that we've emphasized trying to fly over the past couple of years as a part of AFEX. So this is a spiral module. So on the left here, I'm showing you a cartoon of what the P3 could do as you're flying outbound from the eye of a storm, and then you're flying downwind within a rain band. These spirals are indicating that the P3 will essentially start at flight level of maybe 10,000 feet and then spiral upward as high as 20 to 22,000 feet. So it gets above the freezing level, and it takes very valuable measurements of cloud particles, you know, and precipitation particles that are very important, I think, for better understanding what the distribution of these precipitation particles looks like, and how that's represented in numerical models. And so on the right, I'm just showing you some images from probes, precipitation probes from the P3 from one of these spirals. And you can see the temperature here, as indicated, it starts at about 10 degrees Celsius, so well above freezing. And then as the plane ascends, you start to see you know, changes in what the precipitation particles look like. It shifts from rain droplets to you know, to kind of grovel type of particles, and then ice crystals and so forth as you get higher and higher. So really able to detect how the distribution of these particles changes over altitude and over temperature. So one other thing that we're doing, and we've really made an emphasis on, is, you know, we've been flying for decades, right? And we've collected data from, you know, a multitude of storms, and we have a huge database now. And so this database is really just, it's there for the taking. It's there for the research community to really take advantage of. And we've taken advantage of that over the past 10 to 15 years, but, you know, there's a lot that can be done. And so several of our scientists have done a great job at compiling that data and putting it together in forms that are easily used by the research community. This is one example, something called TC Radar. It's a collection of TDR analyses over a 23-year time period, includes over 900 analyses from over 270 flights with a wide range of TC intensities. And so the map is showing you all the different locations of missions for which we have data sets within the TC Radar database. It's in an easy to use format, NetCDF, so, you know, any researcher can use it. And what's nice about this data set is it has not just the information from the radar analyses, but also environmental and storm metadata. So we have information on the vertical shear, sea surface temperature, you know, characteristics of the environment and things like that, storm motion. So all that's, I think, really helpful for any researcher that might want to look at relationships between things like shear and intensity change and so forth. This is just an example of a composite of the vertical cross section of radial and vertical velocity for tropical, you know, weak systems, tropical storms, minor hurricanes, and major hurricanes. And so you can see, you know, the strength of the inflow is the depth of the inflow in the lowest levels decreases as you get stronger and stronger storms. And so, you know, it's just an example of what the capabilities of this type of database. Another database very similar in concept, but with dropsondes, called TC Drops. So this is a database that has accumulated dropsonde data from TC flights since 1996, currently up through 2020, so 24 years. And it's not just NOAA drops and NOAA missions, it's all programs and platforms, whether it's NOAA, Air Force, NASA drops, ONR drops, NCAR, DotStar, so, you know, in Taiwan. So it's truly a global database. It's not just US centric, so it's got West Pacific data as well. Currently over 30,000 drops, and similar to TC Radar, it includes environmental and storm metadata. So this is just a plot here showing you the number of sondes within storms of each intensity category. So you can see, you know, as many as 10,000, you know, close to 10,000, you know, over 9,000, let's say, dropsondes for tropical storms, you know, down to 6,000 drops basically for category 1, and even category 5 hurricanes, we've got over 1,000 dropsondes. So this has a lot of potential, I think, again, for giving us, you know, research opportunities looking at, you know, temperature and moisture distributions, for example, in the lower levels, especially for, you know, storms. So it's again another application that I think is really valuable for the research community. And so last slide here, just talking about what we're looking toward for this year. We're partnering with several different other experiments and taking what I call a global perspective. And so that is, so AFEX is going to operate, you know, primary bases of operations of what I talked about before, you know, out of Lakeland, Florida, and then the Caribbean, St. Croix, Barbados. But we're also going to partner with another NOAA experiment called ITOPS East. And so what that will involve is taking the NOAA G4 east to Cabo Verde, just off the coast of Africa. So you can see on the map here. So the G4 will operate out of Cabo Verde at least for, you know, a week or so. If we identify a system, it'll go out there and sample the environment of pre-genesis disturbances emerging off Africa in August of this year. And then another experiment we're also very excited about is a NASA experiment called CPEX CV for Cabo Verde, and that will have the NASA DC-8. So that's another high altitude jet that'll operate out of Cabo Verde in September, and that will sample the environment and the intercore structure of pre-genesis disturbances in September. And so the idea is to have what we call handshake missions during this month of September, where You can envision the DC-8 flying disturbances that move off of Africa, sampling that for several days as these disturbances are moving west across the basin, and then the P3 and or the G4 out of Barbados could pick up these storms and then essentially continue the monitoring of the system as it evolves and moves over the basin. So it really has a potential for covering the entire Atlantic basin of systems from pre-genesis, I would say, all the way to mature stage and then potentially to landfall. So I don't think that's really ever happened in terms of a basin perspective like this. And so it's very exciting, and we're looking forward to the opportunity for this year. So with that, I believe that's all I have, and I will say thank you and be happy to take any questions.
Thank you, Rob. This has been a deep dive into the aircraft and what it does and how it has improved our research here at the Hurricane Research Division. There's been an exhaustive and animated conversation happening in the chat, so I'm going to sift through a few questions based on our time frame here. Folks have really liked the animations that you've shared. There was a question and there was a dialogue that happened, but I'll share it with you in case you want to chime in. There was a question by Andy Hagan who said, have there been data denial studies that show the benefit of the tail Doppler radar data to HWRF intensity and or structure? I should share that there's a couple of papers that were shared, but I wanted to invite you to give a response to that, Rob.
Yeah, there certainly has been, and obviously some of the responses in the chat. I don't have the chat in front of me, so I can't see it. But yeah, there definitely has been. That's been a big effort. The idea of assimilating tail Doppler radar data into aircraft, or I'm sorry, into mesoscale models, I think started really with Fuqing Zhang back about 15 years ago or so. And those are some of the first pioneering studies that looked at that. And since then, it's become an operational thing, and it's really an important part of what we've been doing. And I know Jason Sipple at HRD has really led that effort on our end to look at the impact of the tail Doppler radar data. And I think it has shown substantial improvement in the intensity forecasting when you incorporate the TDR data. And I think that's especially the case for weaker systems that are perhaps a little bit less organized, that you really, you benefit from the aircraft data to sample and observe what the real structure looks like, not what the model thinks it looks like in the absence of any data. So having that aircraft observation, especially for weak systems, I think is particularly valuable.
Thank you. There's another sort of a wondering question, I guess. This is from Kyle. He says, I have at times wondered whether SST cooled pool wake positions are important. For example, where we expect the boundary layer enthalpy recovery sector to be relative to shear.
Yeah, well, yeah, I think if I understand the question or the comment, yeah, I think that's definitely an important aspect, and that's one of the, I didn't talk about it here, but that is something that we have. There's been papers written on that, not just by us, but lots of other people too, both in an observational and modeling framework. But yeah, definitely where that shear vector sets up, and where that will determine where you get the maximum cooling on that left of shear side, let's say, and then there's questions about will that air recover, right? Will the boundary layer recover by the time the parcels reach the downshear right quadrant, so to speak? So, what governs the situations where it does recover and other times when it doesn't? There was a paper I didn't mention because I didn't have time, but it was another composite study looking at drops-on data, and we found that we looked at the boundary layer structure, and we found that the cases where it did recover and intensify, you had stronger winds on that upshear side, and so you had larger surface fluxes. And, so these types of relationships that we can identify with observations and then also in models, it's a really important aspect of what we do, I think, in advancing our understanding and ultimately prediction.
There's another question that came in. Thank you, Rob. Says, I have a general question about the improvement in HWRF. Is there a way to separate out improvements in resolution for those due to having better data, and which data have the most impact?
Yeah, that's definitely a very important question. And, I touched on it, but maybe I didn't give it the attention that it deserves. But yeah, no doubt that a lot of the improvements in HWRF that I showed were due to improvements in the models themselves, right? And it's not just the aircraft. So there's the resolution improvements, physical parameterization improvements, some of which I think arose out of observations, but others not. But also, it's not just the aircraft data, satellite data and satellite assimilation, improvements to the global models, which provide the boundary conditions, at least for a lot of these regional models like the HWRF. So it's a whole host of factors. And that's not the area that I work on in terms of data impacts, but that's certainly something that we do work on at HRD and elsewhere. And it's definitely something that should be controlled for and examined. I think it already has been. I just don't have the references off the top of my head, but that's certainly something, it's model formulation and model numerics, and as well as the data, how you assimilate that data. That's another biggie, which I didn't talk about any of the data assimilation techniques, and that's a huge part of what produces better forecasts. So, but ultimately, a lot of it comes back to the data itself and the data you collect, and then how you incorporate that data into the model. That I think plays a big role in intensity, or just forecast improvement in general, not just intensity.
Thank you. I should say that Jason Sippel, he chimed in here and he said for HWRF, all the different recon components are contributing. So
right.
To add to your comment there.
Thanks.
Hey, this is Gus. I could chime in too. Can you hear me?
Yes,
Yep.
you can. Go ahead.
Yeah, just real quick, just a minute. So I mean, yes, there is a way to separate them, but a lot of that work hasn't extensively been done, especially in published work, because it's hard to do that. The upgrade cycle sort of requires that these things all be done at once, and so it's hard to tease them out. But to the extent that we found what the resolution improvements do is they allow further improvements by assimilating more data or upgrading physical parameterization schemes. And so, all of these things really are working in concert with one another. And so, it's sort of unfair to sort of say, okay, what benefit are we going to get without changing the resolution, because we're going to do that anyway. So anyway, long-winded answer, but more just supporting what Jason said, where there are multiple different components that are all important here, and they all sort of work in concert.
Thanks, guys.
And one last question here we've got, it says, are you planning to fly over land to address your goals 2 and 3 of AFEX?
Good question. Landfall is, that's always been on the books and something that's been a priority, of course, for us because of its immediate and direct impact on the population. We don't typically fly the aircraft over land in a landfalling scenario for safety reasons. It's ultimately up to the pilot, of course, but we do actually have several different experiments that target the landfall time period. We can fly along the beach, and we have, with our remote sensing measurements, the tail-Doppler radar, for example, we can get information inland. That being said, we also have partnerships, and I really want to strengthen those partnerships, I'd say even more than we already do, at least personally for me, with scientists and researchers that do have instruments that travel on the surface roads, for example, and they have mobile Doppler radars and things like that we do work with them. So ultimately what we need to do, I think, is we need to stitch together or merge or combine the airborne data sets that we collect, both offshore and just as the storm is making landfall, with the data inland that we get from these mobile Doppler radars, as well as the 88Ds and just the fixed stations as well. So kind of the synthesized database of offshore observations as well as inland observations, I think, is what really will allow us to make some progress on some of these questions regarding structural changes at landfall, tornado development, and things like that. I think those are all really important questions, and there's been a lot of great work on it, but I think there's more that we can do.
Thank you, Rob, for this informative seminar, for answering the questions. We are at 3:30, so thank you for those who had a lively discussion on the chat. Thank you for joining, and now we will go ahead and close the seminar. Thank you again for joining. Have a good day.
Thank you, everyone.
Thanks, Rob.